Have you ever looked up at the night sky and felt overwhelmed by the sheer number of stars? We focus on the bright lights, the planets, the nebulae, the enormous star cities we call galaxies. They are the landmarks of our cosmic map. But what happens when you look away from them? What about the vast, seemingly empty gulfs that separate these brilliant islands? We often call it nothing, a vacuum, the void. Yet, perhaps the greatest secrets of the universe are not contained within the light, but hidden in the spaces between. It's a space where density drops to near zero, yet where the rules of cosmology still play out on the largest scale imaginable. What is really there? Does empty truly mean empty? If you enjoy slowing down, thinking big, and exploring the silent, foundational parts of the cosmos, a soft like and subscribe helps this journey reach others like you. Settle in. Let's look past the glow and investigate the invisible web that connects and separates everything. When we look at the universe, our attention naturally fixes on the points of light. We see galaxies, huge, glowing spirals that look like close neighbors scattered across the black. These images, however, hide a profound reality. The distances between these galactic cities are wider than the mind can easily hold. Our own Milky Way galaxy, for instance, has a closest large companion called Andromeda. The light we see from Andromeda tonight has been traveling for approximately 2.5 million light-years. To put that span into perspective, that light began its journey through space long before any human civilization began, long before the first recorded history. Yet, this massive separation is relatively small by the universe's standards. When we move beyond galaxy clusters and into the true voids, the gaps can stretch across hundreds of millions of light-years. In these vast, empty expanses, our most sensitive instruments detect almost nothing. But in the language of physics, the word nothing is always a bit misleading. Even the deepest, darkest voids are not truly absent of everything. They carry the faint signature of matter, energy, and radiation. The space between galaxies is not a perfect vacuum. Rather, it is an almost unnoticeable haze of atoms, particles, and light, all stretched incredibly thin by the continuous expansion of the cosmos. For every cubic meter of that intergalactic medium, we might find only 1 or 2 stray atoms, often hydrogen. This density is so low that the most extreme laboratory vacuums created on Earth feel crowded by comparison. Despite their scarcity, these stray atoms are crucial. They serve as silent witnesses to the universe's history, providing clues about what the cosmos is made of, how structure formed, and how it continues its evolution. The spaces between the galaxies are precisely where the ancient fingerprints of cosmic development are preserved, faint, cold, and scattered, but present for those who know how to search. Imagine positioning yourself within that intergalactic darkness. There would be no nearby stars to warm you, no planet beneath your feet. You would be surrounded only by a black so complete it feels almost physical. The nearest galaxy would appear as nothing more than a faint, distant smear, too far away to cast a single shadow. You would be suspended in the soft, ever-expanding fabric of space itself. While this might sound lonely, it is also fundamentally peaceful. This emptiness is not without order. It holds the structural scaffolding of everything. Astronomers often picture the universe as a type of foam or a 3-dimensional spiderweb, a structure known as the cosmic web. The visible galaxies are gathered along the thin threads of this web, clustering together where the invisible filaments of matter cross. The regions between these intersections are the great voids, vast, bubble-like spaces where very few galaxies reside. These voids are not just holes, they are essential parts of the universe's grand architecture. This cosmic web did not always exist. Immediately following the Big Bang, matter was spread almost uniformly across all of space. Over time, minute fluctuations in density, tiny differences in the amount of matter from one spot to the next, began to amplify under the steady, relentless pull of gravity. Over billions of years, the slightly denser regions successfully pulled in more matter, which eventually led to the formation of stars and galaxies. Conversely, the emptier regions became even emptier. The result is the universe we observe today. Massive filaments of clustered galaxies wrapping around gigantic bubble-like voids that stretch for hundreds of millions of light years. Drifting through one of these voids would be an encounter with near absolute vacuum. The temperature would be just a few degrees above absolute zero. There would be no sound, as there is almost nothing for sound waves to travel through. The only light detectable would be the dim glow of the most distant galaxies, appearing like scattered embers in an endless night. Occasionally, a single hydrogen atom might drift past you. Yet, even in this profound emptiness, physics operates continuously. Photons from the cosmic microwave background, the light remnant from the Big Bang, still pass through. They have been stretched by the universe's expansion until they glow faintly in the microwave range of the spectrum. This light is too dim for our eyes, but is easily detectable by specialized, sensitive instruments. This is a faint, omnipresent signal that even the emptiest spaces retain a memory of the universe's beginning. The vastness between galaxies presents a kind of paradox. It seems to separate everything, yet it is also what connects everything. The same cosmic expansion that creates the enormous distance is what ties all of space together. When galaxies appear to drift apart, they are not primarily moving through space. Instead, they are being passively carried along by the expansion of space itself. Consider dots on the surface of an inflating balloon. The dots are not flying away from a central point, but the distance between them increases because the surface of the balloon, the space between the dots, is stretching. This stretching is key. The farther apart two distant galaxies are, the more space is stretching between them, and the faster their apparent separation increases. Understanding the space between galaxies is therefore crucial to understanding the process that defines the universe's ultimate shape and fate. For most of human history, the existence of these massive gaps was unknown. The night sky seemed crowded with stars. It has only been in the past century that we have learned that the majority of the universe's volume is not filled with stars at all, but with darkness. The galaxies are simply glitter sprinkled on the surface of a truly vast, invisible ocean. And the more we study this ocean, the more we find that it holds the biggest mysteries of cosmology. Some of these mysteries have familiar names now: dark matter and dark energy. These ideas originated from attempts to explain the behavior of the space between the stars. When astronomers calculated how galaxies move within their clusters, they discovered something unexpected. The galaxies were orbiting much too fast to be held together solely by the gravity of the visible matter. There had to be an unseen element, something invisible filling the gaps and binding the clusters with its gravitational pull. This necessity led to the concept of dark matter. Dark matter does not emit light, but it exerts a powerful gravitational force. It is far from rare. In fact, dark matter constitutes the majority of the universe's total mass. It acts like the invisible scaffolding of the cosmic web, holding the massive structures of galaxies in their stable positions. But if dark matter pulls things together, something else must be pushing them apart. Observations of very distant stellar explosions, called supernovae, conducted in the late 1990s, revealed that the universe's expansion was not slowing down as expected. It was, surprisingly, speeding up. This accelerating stretch is attributed to a repulsive force we call dark energy. We still do not know precisely what dark energy is. It might be a fundamental property of space itself, a pressure that is inherent to the vacuum and increases as the universe expands. Or it might be something entirely novel, a new type of energy field permeating the cosmos. Regardless of its true nature, dark energy now dominates the universe, shaping the enormous spaces between galaxies more profoundly than any other known force. Therefore, when we discuss what resides between galaxies, we are truly talking about the arena where dark energy operates, where dark matter constructs its invisible scaffolding, and where the faintest hydrogen atoms drift like small dust motes in an immeasurable room. If you were to point a powerful telescope toward one of those dark, seemingly empty patches of sky and allow it to gather light for days, weeks, or even months, distant light would slowly begin to appear. The Hubble Space Telescope famously performed such an observation, known as the Hubble Deep Field. From a patch of sky no larger than a grain of sand held at arm's length, the telescope collected light from thousands of incredibly distant galaxies. Some of that light began its journey more than 13 billion years ago. What appeared to be total emptiness turned out to be filled with countless other galaxies. But even between those distant galaxies, space dominates light. Most of the universe, by volume, is composed of the in-between, the intergalactic medium, the stretched cosmic web, the dark matter scaffolding, and the fabric of space-time itself. The dazzling galaxies are merely the punctuation marks. The primary story of the universe is written in the vast, silent spaces. As you absorb this idea, you might notice the quiet feeling it brings. Contemplating these immense distances often induces a certain stillness. It is not an emptiness that feels threatening, but one that is calming. These impossible expanses provide a gentle reminder of cosmic scale. The same universe that stretches trillions of kilometers between galaxies can also be held gently within the span of your imagination. As we continue this exploration, we will remain in this dim, quiet region of the cosmos. We will focus on the corridors where the subtle whispers of gravity and the faint echoes of light still shape the whole story. In a profound sense, every galaxy owes its very existence to what lies between them. Without the gravitational pull exerted by dark matter, without the pressure of expanding space, and without the faint gases drifting through the void, these massive stellar structures would never have formed. What we perceive as nothing turns out to be the quiet, fundamental architect of everything. The next time you look up at the night sky, try not to focus only on the brightest stars. Instead, allow your gaze to rest on the dark spaces surrounding them. That darkness is not simply an absence of light. It is the canvas of creation, the place where the universe conducts its most patient and critical work. To understand the scale, it helps to try and visualize the distance to our neighbor, Andromeda, which is about 2.5 million light years. A light year itself is the distance light travels in 1 year, roughly 9 trillion kilometers. This unit is so immense that we often stop trying to picture it. But imagine light, the fastest known entity, streaming through space at nearly 300,000 kilometers per second. Even at this incredible speed, the light requires more than 2 million years to cross the gap between just the Milky Way and Andromeda. Every time the faint glow of Andromeda is visible, you are looking at light that started its journey when early human ancestors were still walking the plains of Africa. Andromeda is only the nearest large galaxy. Most other galaxies are far more separated. If we could step back far enough to view a cluster of galaxies at once, they would resemble islands scattered across an invisible, stretching ocean. This ocean is not made of water or air. It is space-time itself, expanding and carrying the galaxies along with it. In this ocean, there is no boundary, no true center, and no true edge. Wherever an observer stands in the universe, it expands away equally in all directions. The increasing distance between galaxies is due to the growth of space between them, not the movement of the galaxies through space. This concept is challenging for the human mind, which is accustomed to thinking of movement as travel. But here, the background itself is stretching. Every second, the underlying fabric of the universe adds distance between separated galaxies. This explains why the farther away a galaxy is, the faster it appears to be moving away from us. The galaxy is not accelerating like a rocket. The space separating us is simply expanding at a greater rate across larger distances. Astronomers measure this stretching by observing the light from distant galaxies. As light travels through expanding space, its wavelength is also stretched, causing a phenomenon known as redshift. The more distant the galaxy, the more its light is shifted toward the red end of the light spectrum. By carefully measuring this shift, scientists can calculate the galaxy's distance and the rate at which space has expanded since that light was emitted. It is similar to studying a photograph that has been slowly stretched over billions of years and understanding the universe's expansion from the distortion of the image. These observations have confirmed that galaxies are not randomly placed. They form groups and clusters connected by thin filaments of matter, like the threads of a vast web. Between these clusters are the immense voids, regions of near emptiness, sometimes hundreds of millions of light-years across, containing hardly any galaxies. These voids are the closest the universe comes to a pure vacuum. It is difficult to describe such vastness in familiar terms. If our Milky Way galaxy were shrunk down to the size of a small coin, the nearest comparable galaxy would be located several large cities away. The next major cluster of galaxies, the Virgo cluster, would be thousands of kilometers beyond that. The great cosmic voids between them would stretch across entire continents. These are distances that render our fastest human-made spacecraft virtually motionless. The Parker Solar Probe, the fastest probe ever launched, moves at about 700,000 kilometers per hour. At that speed, it would still take more than 40 billion years to reach Andromeda, a time span longer than the current age of the universe. The space between galaxies is, for all practical purposes, unreachable by physical means. These are places we can only explore through the light they transmit, through mathematics, and through the patient accumulation of data. Yet, these unreachable distances fundamentally define the shape of everything. The universe has its current structure because of the spacing between galaxies, not just because of their clustering. If galaxies were packed more closely, the entire sky would glow with their light, and darkness would be rare. If they were farther apart, there might not be sufficient gravitational pull to form large structures at all. The quiet architecture of the universe, its profound balance, relies entirely on the precise amount of distance found between these massive collections of stars. It is a strange concept, The vast majority of the cosmos is space, not tangible matter. If one could theoretically gather every star, every planet, every grain of dust, and every atom of gas, and compress it all into one location, the universe would still be almost completely empty. The galaxies themselves, enormous as they appear, take up a nearly negligible fraction of the universe's total volume. Most of everything is distance. Most of existence is the in-between. This distance, however, is not spread uniformly. The distribution of galaxies across the cosmos is fundamentally uneven. In certain regions, galaxies cluster with such density that they form massive structures called superclusters, gravitationally bound groups of clusters that can stretch across hundreds of millions of light years. Between these superclusters lie the great cosmic voids. These voids are more than just dark. They possess a subtly different physical environment. The temperature, the density of matter, and even the background radiation levels shift slightly. Space here is perceptibly thinner, colder, and quieter. Were you to drift into one of these voids, the nearest galaxy might be so distant that its light would appear merely as a faint, motionless pinprick, no brighter than a regular star. And yet, there is constant motion everywhere. Even across these unimaginable distances, galaxies are never perfectly still. They move under the complex, combined influence of gravity. Within clusters, they drift toward each other, being pulled by the unseen threads of dark matter. Some galaxies, like our own Milky Way and Andromeda, are slowly falling together, set on a course to merge billions of years from now. Others are drifting apart forever, carried by the expansion of the universe faster than the force of gravity can reel them back. When we attempt to visualize these distances, it is easy to forget that light itself requires time to travel. Every time we look at a distant galaxy, we are essentially looking backward through time. The farther away the galaxy is, the older the image we receive. Some of the faintest, most challenging smudges observed through powerful telescopes show us the universe as it was only a few 100 million years after the Big Bang. The light from those ancient galaxies has traveled for more than 13 billion years, crossing and being stretched by continuously expanding space. This means that, in a practical sense, much of the universe we are observing no longer exists in the exact configuration we are seeing. The galaxies have moved, merged, and changed. Their light is truly ancient history. Between us and those distant galaxies lies the intergalactic space, which is cold, thin, and nearly empty, but it is not entirely devoid of matter. In the earliest universe, this space was filled with hydrogen gas, the residue left over from the Big Bang. Over the passage of billions of years, much of that gas was drawn into forming galaxies where it fueled star creation. However, some gas remained behind, stretched thin between the galaxies, and ionized, meaning its electrons were stripped away by the intense radiation emitted from early stars and quasars. This leftover substance is called the intergalactic medium. It is still present, filling the voids with a faint, ghostly presence. When light from distant quasars passes through it, it leaves subtle fingerprints in the light's spectrum, faint absorption lines that provide precise information about the gas's chemical composition and temperature. These fingerprints allow astronomers to map invisible matter across billions of light years. They demonstrate that even the seemingly emptiest regions are interconnected by a tenuous network of gas and plasma, effectively forming the structural skeleton of the universe. Where the gas is marginally denser, galaxies formed. Where it remained thinner, the voids persisted. The enormous spaces between galaxies are therefore not truly barren. They are woven with filaments of gas, dust, and dark matter, all so faint they are almost impossible to detect directly. As we contemplate those distances, it is important to remember that space itself is not static. The rate of expansion, which we call the Hubble constant, dictates how fast galaxies move away from one another. For decades, astronomers have attempted to measure this rate with extreme accuracy. The results, however, vary slightly depending on the measurement technique used. The underlying scientific debate is not just about the numbers. It concerns what those numbers reveal about the universe's true age, its composition, and its ultimate fate. If expansion continues to accelerate under the influence of dark energy, then the distances between galaxies will become so great that in the far future, most galaxies will eventually drift beyond the observable horizon. Their light will never be able to reach us again. The night sky will effectively grow emptier. Future observers, living in a single, isolated galaxy far in the future, might look out and see only darkness, completely unaware that billions of other galaxies ever existed. This realization, while immense in scope, provides a vital context. The spaces between galaxies are not just voids. They are the necessary condition for structure. Without the emptiness, there would be no contrast, no boundaries, and no room for galaxies to exist separately. Space is not just what lies between objects. It is what allows things to be separate, to possess shape, and to exist at all. The more we study these immense separations, the more we recognize how subtly interconnected everything remains. Galaxies may appear isolated, but they were all born from the same early universe, shaped by the same forces and bound by the same invisible threads of gravity. Across distances that light itself struggles to cross, the laws of physics remain perfectly consistent. The same patterns repeat at every scale, from the swirl of gas on a planet to the spiral arms of a galaxy. The distances between galaxies might be beyond intuitive comprehension, but they do not break the continuity of the universe. They define it. They are part of its fundamental rhythm, the slow, persistent pulse of expansion and separation that has been unfolding for more than 13 billion years. As we drift further into this story, we keep that massive sense of scale in mind. Between every shining cluster lies the true body of the universe, the distance itself. It is not nothing. It is the silent stage upon which everything else performs, and the more attentively we learn to listen to that silence, the more it begins to reveal its story. When scientists first began mapping the universe in detail, their goal was to determine where galaxies were, how they were arranged, and their speeds. Telescopes collected light from tens of thousands of galaxies, each one marked as a tiny point on a cosmic chart. Initially, the data appeared random, like dust scattered across a table. But as the surveys grew in size, an unexpected structure began to appear. Faint, repeating patterns. Galaxies were not evenly spread. They were arranged in long, interconnected strands forming clusters, filaments, and knots that wound their way through enormous empty regions. The universe was not a smooth sea of matter. It was textured, patterned, and highly organized. This fundamental pattern became known as the cosmic web. The term is entirely literal. On scales spanning hundreds of millions of light years, matter in the universe forms this web-like network. Galaxies, clusters, and superclusters are strung along long, thin filaments of dark matter and gas, while the enormous, empty spaces, the voids, lie between them. It is as if the universe used gravity and time to weave its own vast, delicate web, stretching threads of matter from one cosmic region to another. To understand why this happens, we must return to the earliest period of the universe, just after the Big Bang. At that time, space was extremely hot, dense, and nearly uniform. There were no galaxies, only an expanding soup of particles and radiation. However, within that uniformity, tiny imperfections existed. Some regions were infinitesimally denser than others, perhaps by only 1 part in 100,000. Over billions of years, gravity relentlessly amplified those differences. The denser areas naturally attracted more matter, growing heavier and drawing in nearby material, while the emptier areas became emptier still. Out of that slow, gravitational dance, the large-scale structure of the universe took its complex shape. Computer simulations beautifully illustrate this process. When cosmologists input the known early conditions of the universe into powerful models and allow them to evolve according to the known laws of physics, the results are astonishing. The simulated universe spontaneously develops a web-like pattern that closely matches what astronomers observe through their telescopes. The clusters and filaments naturally appear as gravity pulls matter together along the invisible threads of dark matter. The vast voids open up between them, hollow regions surrounded by the glowing walls of galaxies. What began as a nearly uniform fog of particles eventually became the cosmic tapestry, the largest known structure. Dark matter plays the central, starring role in this formation. Although it is entirely invisible, it constitutes most of the universe's matter content, about 5 times more mass than the ordinary matter that forms stars and planets. Dark matter does not interact with light or electromagnetism, but it fully responds to gravity. It clumps together under its own pull, forming the large halos and filaments that act as the structural scaffolding for the entire cosmic web. Ordinary matter, the gas and dust that eventually form galaxies, simply collects along these pre-existing structures, settling into the deep gravitational wells carved out by dark matter. In this sense, the visible universe is a kind of shadow, tracing the outlines of dark matter's unseen architecture. Astronomers have developed clever ways to map these hidden structures. One key method uses the bending of light, known as gravitational lensing. When light from distant galaxies passes near massive regions of dark matter, its path is subtly bent, slightly distorting the image we receive. By carefully studying these distortions across large areas of the sky, scientists can effectively reconstruct the precise locations where the invisible mass lies. These resulting maps consistently show the same familiar web pattern, a network of filaments connecting clusters of galaxies across billions of light years. This structure is so consistent that it is frequently called the backbone of the universe. If it were possible to see the cosmic web with the naked eye, it would be one of the most magnificent sights imaginable. Picture an enormous, 3-dimensional lattice, glowing faintly in the regions where galaxies gather, but fading into transparency as the filaments stretch away into the void. Some filaments span hundreds of millions of light years, thin as threads yet gravitationally powerful enough to shape entire clusters. The intersections, or nodes, where several filaments meet, are where the most massive structures form, superclusters containing thousands of galaxies. Between them, the empty voids open up like vast dark bubbles, each one millions of light years across. The structure is both vast and incredibly delicate. the average density of matter within its filaments is still extremely low, far lower than any vacuum we could create on Earth. The gas flowing along these filaments is so thin that a single cubic meter might contain only a few atoms. Yet, over the scale of hundreds of millions of light years, that faint presence accumulates enough mass to influence the motion of galaxies and to act as a gravitational bridge between clusters. The filaments also function as the highways of cosmic evolution. Gas flows along them and into galaxy clusters, providing the fuel necessary for star formation and feeding supermassive black holes. Some astronomers view the web as a kind of circulatory system for the universe, constantly redistributing matter and energy. Without these flows, galaxies might have run out of material to form new stars billions of years ago. Instead, the cosmic web ensures the universe remains dynamic even as it grows older. As we observe deeper into the universe, and therefore further back in time, we can see earlier versions of this web in the process of formation. The most distant galaxies ever found lie along primitive filaments that were still taking shape only a few 100 million years after the Big Bang. The pattern was already present, confirming that gravity began its patient work, sculpting the universe from near uniformity into complexity, a process running uninterrupted for more than 13 billion years. The universe is interconnected. The web connects every galaxy, every cluster, and even every single atom of intergalactic gas through gravity and the shared history of cosmic expansion. You could travel in any direction for billions of light years and still be moving within the same vast network of connections. There is no external boundary. The web fills the entire observable universe. The cosmic web also offers crucial information regarding the universe's eventual fate. Since dark energy is actively driving expansion, the web's filaments are slowly but surely being stretched. Over the next billions of years, galaxies located within clusters will remain gravitationally bound together, but the spaces between these massive clusters will grow continuously wider. The web will become thinner, its strands pulled taut until, eventually, the most distant filaments recede beyond the visible horizon. The overall large-scale structure will endure, yet it will become far more diffuse, quieter, and its evolution will slow down. In a profound sense, the web is both the skeleton of the universe and its patient, slow heartbeat. For now, though, we can still observe its immense structure. With powerful new instruments like the James Webb Space Telescope and deep surveys utilizing radio, X-ray, and optical wavelengths, scientists are mapping more of the cosmic web than ever before. Some of the most recent observations have even detected faint, actual glows of gas along the filaments themselves. These are the first direct glimpses of the basic material that binds the cosmic structure together. Seeing these delicate threads of hydrogen stretching across the gaps between galaxies is akin to seeing the fundamental bones beneath the universe's surface. It confirms that even the spaces that appear completely dark are part of something structured, organized, and functioning in its own slow gravitational way. When we consider that vast web, it presents a clear illustration of cosmic balance. The bright regions, the galaxies, stars, and nebulae are the visible expressions of structure. However, they exist only because of the dark, invisible framework that supports them. Without the filaments made of dark matter, galaxies would inevitably drift apart like scattered dust. Without the vast cosmic voids, there would be no necessary contrast to clearly define the clusters. The universe's entire structure and visual character come from this fundamental interplay. matter and emptiness, connection and separation, light and darkness. This web is not a mechanism designed by human intelligence. There is no center, no edge, and no intentional purpose woven into its threads. But when viewing the maps and simulations, the resemblance to networks found elsewhere in nature is clear. The universe appears to have adopted a natural geometry, a form that repeats across scales from the smallest subatomic networks to the largest cosmic structures. Whether this similarity is mere coincidence or reflects a deeper unifying principle of physical law remains an open question. It's important to remember that we are intrinsically part of this structure. Our own galaxy resides on one of these filaments, connected by gravity to others across unimaginable distances. The atoms that compose your body were forged in stars that trace their history back through billions of years of cosmic structure. Every element, every particle is tied to that web. You are not standing outside of it, observing from afar. You are within it, a small, complex expression of the same cosmic pattern. The next time you view the night sky, try to think of it not as a collection of isolated points, but as a single, interconnected structure stretching across all of existence. Every star, every galaxy, every speck of light is part of the same web, bound together by invisible threads of gravity and time. The spaces between may seem empty, but they are dynamically connected. In a universe built predominantly of emptiness, the web is the only thing that provides structure. It transforms endless distance into order. It reminds us that even in the most silent stretches of space, something invisible is continuously holding everything in place. If the cosmic web forms the structure of the universe, then the great voids are its empty spaces, the vast, quiet rooms between the walls. They are the most expansive regions in existence and simultaneously the loneliest. When astronomers first began to realize that such enormous gaps existed, it challenged long-held assumptions. For a long period, the universe was conceptually modeled as a uniform field of galaxies spread more or less evenly across space. But as observational maps became better and data deepened, these empty spots began to dominate the visual picture regions, often hundreds of millions of light-years wide, where almost nothing seemed to exist. The conclusion was unavoidable. The majority of the universe's volume is not filled with galaxies at all. It is made up of these colossal, dark hollows. A cosmic void is entirely unlike the empty space between stars within a galaxy. A void is a region where galaxies are simply extremely scarce. There might be a few isolated galaxies scattered within, but they are spread across such enormous distances that, from any one of them, the rest of the universe would look painfully remote. The light from the nearest neighboring galaxy could require tens or even hundreds of millions of years to arrive. These truly are the quietest neighborhoods in all of creation. The largest known voids are colossal structures with names that suggest their vastness, like the Boötes void, the local void, and the Eridanus supervoid. Each one is a huge ocean of near-nothingness, encircled by the walls and filaments of galaxies that constitute the cosmic web. The Boötes void, for example, is roughly 330 million light-years across. Inside that immense region, astronomers have found only a few dozen galaxies. To illustrate this sparsity, in a region of that size, elsewhere in the universe, one would expect to find tens of thousands of galaxies. This pronounced absence naturally demanded a scientific explanation. Over time, computer simulations of cosmic evolution provided an answer. As the universe expands, regions that begin even slightly less dense than average tend to lose matter to their denser surroundings. Gravity consistently pulls material toward the denser areas, the filaments and clusters leaving the lower density regions even more depleted. Over billions of years, these small initial differences amplify, creating deep voids surrounded by dense walls. Therefore, the great voids are not flaws in the universe's design. They are a direct, natural consequence of how gravity and expansion interact. The universe builds its structure by actively separating fullness from emptiness, creating contrast on the grandest scale possible. Standing at the edge of a void, the view would be extraordinary in its simplicity. Looking one way, you would see the crowded filaments, luminous strings of galaxies glowing faintly, gathered into bright clusters, shining against the dark. Turning the other way, you would see almost nothing. No stars, no visible galaxies, just blackness, extending so far that your eye could never find an end point. The temperature deep inside a void would hover near the cosmic background temperature, about 2.7 degrees above absolute zero. This is significantly colder than any vacuum chamber that can be created on Earth. There is no sound, no air, and only the faint hum of radiation left over from the Big Bang, which has been stretched into microwaves by the expanding universe. And yet, even this near-perfect emptiness is not truly empty. Between the scarce galaxies in a void, there are stray atoms, primarily hydrogen and helium, along with the occasional particle of dark matter. The density is so incredibly low that measuring it in ordinary terms is almost meaningless. In some of the emptiest regions, one might find only one atom in every 10 cubic meters. That is a vacuum so extreme that if you filled a room with it, it would take centuries for a single atom to drift from one side to the other. Still, those atoms are real, and they matter. They help astronomers track how gas moves through the cosmic web and how galaxies at the edges of voids evolve differently from those in crowded regions. Galaxies located near the boundaries of voids tend to be smaller, bluer, and richer in gas. With fewer massive gravitational neighbors pulling on them, they evolve more slowly, forming stars over extended periods of time. It is as if the emptiness itself provides them with a quieter, more leisurely existence. Deeper inside the voids, the isolated galaxies sometimes appear as faint, irregular shapes, strange, lonely systems with minimal structure. They drift through a darkness so complete that they may never encounter another large galaxy. In these places, cosmic time operates on scales so vast and slow that the very concept of change begins to feel abstract. Researchers study voids not primarily for what little they contain, but for what they reveal. Because these regions are dominated by the effects of expansion rather than by the local pull of gravity, they function as natural laboratories for testing cosmological theories. The way light travels through a void, how it bends or stretches, carries crucial information about the universe's overall composition, specifically the amounts of dark matter, dark energy, and normal matter. Voids also help to test the accuracy of general relativity across the largest possible scales. If gravity were to behave differently across such enormous distances, the growth and shape of the voids would expose it. The size and distribution of voids also inform us about the universe's history. The small ripples in density recorded in the cosmic microwave background are the initial seeds from which today's voids and filaments grew. By comparing the patterns of those early ripples to the structure of modern voids, astronomers can verify how the universe has evolved over billions of years. Every void is unique, shaped by the surrounding filaments that enclose it. The boundaries are not sharp walls, but gradual transitions where the density of galaxies slowly increases. Even in the largest voids, faint threads of gas and dark matter still weave through, connecting one edge to another. These faint traces link the emptiest regions back to the cosmic web, reminding us that even the most isolated spaces are part of the universal whole. In essence, voids are the universe's most honest regions. They represent what happens when gravity and expansion are allowed to operate without interference. Where there is matter, gravity binds and shapes. Where there is little matter, expansion takes over, stretching space until it thins into near nothingness. It is a fundamental balance. Gravity gathers, expansion disperses, and the voids are the result of that delicate equilibrium. To grasp the pervasive nature of these regions, consider that if you randomly selected a point in the universe, the chances are high that you would find yourself inside a void. That is how dominant they are, by volume. The luminous parts of the universe, the galaxies, are like the foam on the crest of an unimaginably vast wave. The rest, the deep troughs and open water, is the emptiness in between. The places we can see most clearly, the galaxies, are the exceptions. The rule, the dominant reality of the cosmos, is absence. But that absence is not meaningless. It is a necessary part of the structure. Without the voids, the filaments could not stand out. Without emptiness, fullness could not exist. Astronomers use the term cosmic web void network, a phrase that precisely captures both the emptiness and the structure that defines it. The voids and the web are inseparable. This balance shapes the large-scale geometry of everything. It is a process that continues even now. The universe is still expanding, still deepening its voids, and still drawing matter into clusters. When we contemplate these enormous spaces, we can view them not just as places where nothing exists, but as where fundamental potential resides. The emptiness within the universe is far from a passive background. It is full of physical possibility. It serves as the primary stage upon which cosmic evolution unfolds, being the necessary condition that allows light to travel, galaxies to move, and the expansion of space to occur. Even the profound silences of the universe are not absolute. Radiation left over from the early cosmos still permeates them, acting as a constant, faint whisper from the beginning of time. Neutrinos, the lightest and most elusive of particles, pass through them by the trillions every second, flowing unimpeded. Occasionally, a single, lonely photon crosses the void, traveling for billions of years before finding an instrument sensitive enough to notice it. To that photon, the void is simply the undisturbed path home. The voids may be visually dark, but they are transparent. They allow the universe's oldest light and radiation to pass freely, carrying crucial information across unimaginable distances. While to us, even the star closest to our sun feels impossibly distant, the gaps within the great cosmic voids make those stellar separations seem infinitesimally small. Our entire home galaxy could fit thousands of times over inside just one of the larger voids. These regions are too vast, and the processes within them are too slow to change in any way we could ever witness directly. Still, the knowledge that they exist fundamentally changes how we think about the universe. It reminds us that emptiness is not the same as nothingness, and that space itself is an active, evolving participant in the story of creation. The voids demonstrate that even in the complete absence of visible matter, the universe continues to evolve and shape itself. Their quiet persistence gives definition and meaning to everything else. The structure possesses a quiet rhythm. Gravity, expansion, and time work together consistently, shaping the cosmos for more than 13 billion years. In the grander sense, we are inhabitants of the spaces between, living within one tiny filament, looking outward into the darkness that gives meaning to light and allows the universe to expand. If you were to look out and count everything visible in the universe, stars, planets, and galaxies, you would only be accounting for a small fraction of what truly exists. Most of the universe is fundamentally invisible. It does not glow, reflect, or absorb light in any way that we can detect. We call this unknown substance dark matter. The name is scientifically precise. It is called dark because it does not emit or interact with light or electromagnetism. It is called matter because it exerts gravity and possesses mass. Crucially, it is the structural framework around which the visible universe is built. Without dark matter, galaxies as we recognize them could not exist. Their stars would simply drift apart. Dark matter is the hidden thread that binds the universe together, holding everything in place while remaining completely unseen. The evidence for its existence began almost a century ago. In the 1930s, astronomer Fritz Zwicky, while studying the Coma cluster of galaxies, observed that the galaxies were moving with speeds that demanded far more total mass than could be accounted for by the light they emitted. Something unseen was providing extra gravitational pull. He hypothesized the existence of Dunkel materia, or dark matter. This initial idea gained traction later. In the 1970s, astronomer Vera Rubin and her colleague Kent Ford provided compelling evidence. They found that stars on the outskirts of galaxies orbit just as fast as those near the center. This observation implied that a massive, invisible halo of mass surrounded each galaxy, extending far beyond the visible starlight. This pattern was confirmed repeatedly in galaxy after galaxy. Today, the evidence is overwhelming. Observations of galaxy rotation, cluster movement, the bending of light via gravitational lensing, and the patterns in the cosmic microwave background all independently point to the same conclusion. Roughly 85% of all matter in the universe is dark matter. Ordinary, luminous matter accounts for only a small remainder. Most of the cosmos is shaped by this unseen substance. Dark matter, though invisible, actively and powerfully sculpts the universe through gravity. When scientists use computer simulations to model cosmic evolution, they find that dark matter forms the definitive backbone of structure formation. It gathers first under its own gravity, creating immense halos and long filaments. Ordinary matter then falls into these pre-existing structures, cooling and condensing to form the stars and galaxies we see. The visible universe, therefore, traces the shape of dark matter's skeleton. What dark matter is made of remains the most critical, unsolved question in modern physics. Theories suggest it could be exotic, heavy, slow-moving particles, like WIMPs, weakly interacting massive particles, or lighter, wave-like particles, such as axions. Despite decades of building extremely precise underground detectors and sensitive telescopes, no definitive direct signal has been found. The inability to detect it directly only deepens the mystery of its true identity. Even without knowing its composition, we can trace its influence with high precision. gravitational lensing, the distortion of light from distant galaxies as it passes near massive structures, allows astronomers to map where the invisible mass lies. These resulting maps consistently show the familiar cosmic web structure, filaments connecting clusters and wrapping around vast voids. These dark filaments stretch across hundreds of millions of light years, confirming that the universe is bound together by an invisible scaffold. Our own Milky Way is encased in a vast, spherical halo of dark matter that extends for hundreds of thousands of light years beyond its visible edges. This halo dictates the galaxy's stable rotation and influences the motion of nearby satellite galaxies. The Earth, the Sun, and every star we see are constantly moving through this unseen sea of dark matter. Dark matter's peculiar characteristic is its non-interactive nature. It seems to respond only to gravity. It does not absorb or emit light, and it barely collides with itself or with normal matter. This means its particles can pass right through entire galaxies without slowing down, forming diffuse, stable halos over cosmic time. This quiet stability reminds us that not all fundamental things that matter can be seen. Dark matter has a crucial, opposing relationship with the universe's other great unknown, dark energy. While dark matter pulls things together through gravity, dark energy pushes them apart by accelerating the expansion of space. These two unseen forces act in continuous opposition, shaping the large-scale geometry of the cosmos. Dark matter's gravity slows expansion locally, allowing clusters to form, while dark energy's pressure accelerates it globally, stretching the space between those clusters. The present-day universe is a dynamic snapshot of the equilibrium between attraction and expansion, a balance billions of years in the making. Evidence for this choreography is dramatically visible in cosmic events. Even violent galaxy collisions follow dark matter's script. When two galaxies merge, their visible stars and gas collide intensely, but their dark matter halos pass straight through one another, almost untouched. The visible galaxies crash and deform, while the invisible halos slide together, merging slowly into a new, larger structure. The famous bullet cluster is a key example, where the gravitational mass, composed mostly of dark matter, is clearly separated from the colliding hot gas. This observation is one of the clearest demonstrations that dark matter is a distinct, non-interacting substance, separate from the ordinary matter we know. The overall picture is definitive. The universe is not made primarily of what shines, but of what does not. The luminous parts are merely the visible peaks of a much deeper hidden landscape. Beneath every galaxy, every cluster, and every cosmic filament lies the quiet gravitational foundation of dark matter. It is the hidden architecture upon which the visible universe is built, and its only voice is gravity. If the cosmic web is the visible structure of the universe, then the great voids are its essential empty spaces. They are the most expansive regions in existence and are also the loneliest. When astronomers first realized these gaps existed, they challenged the old idea of a uniformly spread universe. Maps now show that the majority of the universe's volume is not filled with galaxies. It is made up of these colossal, dark hollows. A cosmic void is a region where galaxies are extremely scarce. The light from the nearest neighboring galaxy could require tens or even hundreds of millions of years to arrive. The largest known voids, like the Boötes void, can measure roughly 330 million light-years across, containing only a few dozen galaxies where thousands would normally be expected. This absence required a scientific explanation. Computer simulations confirmed that as the universe expands, regions that start out even slightly less dense than average lose matter to their denser surroundings due to gravity. Over billions of years, these small differences amplify, creating deep voids surrounded by the dense walls of the cosmic web. The great voids are therefore a natural consequence of how gravity and expansion interact. Within a void, the temperature hovers near the cosmic background temperature, about 2.7 degrees above absolute zero. There is no sound, no air, and only the faint hum of radiation from the Big Bang. Yet, even this near-perfect emptiness is not truly empty. Between the scarce galaxies, there are stray atoms, mostly hydrogen and helium, along with the occasional particle of dark matter. The density is so incredibly low that in some of the emptiest regions, one might find only one atom in every 10 cubic meters. Galaxies located near the boundaries of voids tend to be smaller, bluer, and richer in gas. With fewer massive gravitational neighbors, they evolve more slowly, granted a quieter, more leisurely existence by the surrounding emptiness. Isolated galaxies deep inside the voids appear as faint, irregular shapes, drifting through a darkness so complete that they may never encounter another large galaxy. Researchers study voids because they are dominated by the effects of expansion rather than by the local pull of gravity. They function as natural laboratories for testing cosmological theories. The way light travels through a void carries crucial information about the universe's overall composition, specifically the amounts of dark matter, dark energy, and normal matter. Voids also help to test the accuracy of general relativity across the largest possible scales. The size and distribution of voids inform us about the universe's history. By comparing the patterns of the early density ripples in the cosmic microwave background to the structure of modern voids, astronomers can verify how the universe has evolved over billions of years. The voids and the web are inseparable. The voids are the result of a delicate equilibrium. Gravity gathers, expansion disperses. To grasp their pervasive nature, consider that if you randomly selected a point in the universe, the chances are high that you would find yourself inside a void. The luminous parts of the universe are the exceptions. The rule, the dominant reality of the cosmos, is absence. But that absence is not meaningless. It is a necessary part of the structure. The cosmic web void network is the phrase that captures both the emptiness and the structure that defines everything. When we contemplate these enormous spaces, we view them not just as places where nothing exists, but as where fundamental potential resides. Through gravity, the presence of dark matter speaks across the entire cosmos. As we consider this, the concept of dark matter fundamentally changes how we imagine space itself. The universe is not just a scattering of galaxies across emptiness. It is a finely woven structure with invisible filaments binding everything together. Every star we see, every planet, and every atom is held in place by this unseen web. The universe is not simply floating apart. It is hanging in a vast gravitational tapestry that stretches from one end of the cosmos to the other. Even here on Earth, we are part of that invisible structure. Every moment, countless dark matter particles, whatever they may be, are passing through you, through the ground beneath your feet, and through the entire planet without leaving a trace. They have been doing so for billions of years, indifferent to our presence, yet absolutely vital to our existence. Without them, there would be no galaxies, no stars, no planets, and therefore, no life. It is strange, yet scientifically grounding, to realize that the universe is mostly made of something unseen. We live surrounded by a fundamental mystery, supported by forces that work quietly, invisibly, without ever drawing attention. It is a clear reminder that the foundation of reality does not always announce itself. Sometimes, the most essential parts of existence are the ones that never make a sound. If dark matter is the unseen hand that holds the universe together, then dark energy is the invisible breath that continuously pushes it apart. It is the quietest force imaginable, yet it absolutely dominates the cosmos. Wherever galaxies drift, and wherever light travels, this subtle energy stretches space itself, actively expanding the distances between everything that exists. It does not roar, it does not rush. It simply continues its work, slow, steady, and unstoppable. For most of human history, the universe was assumed to be static, or, once expansion was confirmed, it was assumed that this expansion must be slowing down. Gravity, after all, pulls things together, meaning every galaxy's mass should gradually decelerate the outward motion. That was the expectation until the late 1990s, when astronomers measuring distant supernovae found something entirely different. The light from those supernovae did not match a slowing universe. It matched one that was speeding up. The expansion was not weakening, it was accelerating. Space itself was stretching faster than before, as if some hidden pressure were pushing it outward. This discovery was unexpected, but the evidence grew stronger. Observations of the cosmic microwave background, the distribution of galaxies, and the behavior of large-scale structures all confirm the same truth. The universe is expanding at an ever-increasing pace. The name given to the cause of that acceleration is dark energy. Like dark matter, it is a placeholder, a label for something we do not yet fully understand. What we do know is that it makes up about 70% of the universe's total energy content. This means the majority of what exists is not matter at all, but this mysterious energy woven into the very fabric of space itself. The simplest scientific explanation comes from Albert Einstein's equations of general relativity. Early in their formulation, he included a term called the cosmological constant, a kind of built-in energy of empty space. Decades later, this same idea returned, reinterpreted to explain dark energy. In this model, the cosmological constant represents a property of space itself, an energy density that remains constant even as space expands. This idea is deceptively simple. Empty space is not truly empty. Even in the absence of matter and radiation, the vacuum possesses energy. As the universe expands, the amount of space increases, and because the energy density remains constant, the total energy increases as well. This continuously drives the expansion to accelerate. It is as if the universe is being gently inflated by its own emptiness. Quantum mechanics complicates this, as calculations for the energy contained in the quantum vacuum yield an absurdly large result, many orders of magnitude greater than what we actually observe. Somehow, the true value of dark energy is vastly smaller than theory currently predicts. Other theories suggest dark energy could be something dynamic, a field that evolves over time, rather than a constant property of space. For now, all observations point to the same reliable outcome. Dark energy is real, pervasive, and steady. It fills every cubic meter of space, from the depths of intergalactic voids to the corners of our own galaxy. It does not cluster or gather like matter does. Instead, it acts uniformly everywhere, stretching the universe evenly in all directions. Its strength is so slight that it has no noticeable effect on small scales. It does not pull at the Earth or even the galaxy, but on the largest scales, where distances reach billions of light years, its influence dominates everything. To grasp this influence, imagine the universe as a vast elastic fabric. Galaxies are embedded in this fabric, carried along as it stretches. Dark energy is the force that drives that stretching. Over billions of years, it has been increasing the separation between galaxies, pushing them apart faster and faster. The galaxies themselves do not feel this motion locally, as their own gravity binds them together, but the space between clusters of galaxies keeps widening. Over very long timescales, this gentle acceleration has profound consequences. As the expansion continues, galaxies that are now visible will drift farther away. Eventually, their light will be redshifted so significantly that it fades from view entirely. Billions of years from now, distant galaxies will slip beyond the cosmic horizon, the limit beyond which light will never be able to reach us, no matter how long we wait. To future observers, the universe will appear much emptier than it does today. Only the closest galaxies, gravitationally bound to one another, will remain visible. Everything else will recede into an unreachable darkness. This future is often called the era of isolation. It is a slow fading of cosmic connection, caused not by destruction, but by expansion. Space itself grows so vast that communication between distant regions becomes impossible. It is not a catastrophic end, but a quiet drifting apart, the universe expanding into solitude. Dark energy is paradoxical. It is the dominant force in the universe, yet it is the least tangible. It acts everywhere at once, equally and invisibly. It does not concentrate. Its calm persistence and quiet steadiness are part of what makes it so mysterious. For cosmologists, studying dark energy is an exercise in subtlety. It cannot be measured directly, but its effects are clearly inferred through careful observation. One approach is to map the large-scale distribution of galaxies over time, as the rate at which structures form and grow is influenced by the balance between gravity and dark energy. Another method relies on distant supernovae, which act as standard candles to reveal how quickly the universe expanded at different epochs. So far, all independent evidence supports an accelerating universe. There is a quiet elegance to the way these measurements converge. The cosmos is dominated by a smooth, persistent energy that resists compression and drives expansion. It acts not like ordinary matter, but like a property of the vacuum itself. Even though dark energy defines our universe, it has no clear origin story. We can trace matter and radiation back to the Big Bang, but dark energy simply seems to have been there all along. This can be unsettling. It means that space is not nothing. It has weight, energy, and behavior. It is dynamic, capable of stretching and growing. When we say the universe is expanding, we are not talking about galaxies moving through a pre-existing void. We are talking about the void itself changing. Every second, new space comes into being, and dark energy is the quiet reason why. This process is happening everywhere, even here. The space between you and the nearest star is expanding too, though so minutely that local gravity cancels the effect. The same expansion that stretches the universe on the grandest scales is also present in the smallest gaps between objects. It is an omnipresent property of reality itself, imperceptible locally, but decisive globally. When cosmologists model the far future, they find that dark energy will likely continue to dominate. The current era, in which galaxies still gather and stars still form, is temporary. As time passes, expansion will dilute the matter content of the universe, weakening gravity's influence on large scales. Eventually, only the structures bound by their own gravity, individual galaxies and local clusters, will remain intact. Beyond them, the universe will grow darker, colder, and emptier. This transformation is not a catastrophic finale, but a gradual shift into stillness. Dark energy, for all its mystery, may be the reason we have this particular kind of universe, one that lasts, one that grows, and one that allows structure to form before slowly letting it drift apart. The fact that such a quiet, invisible force shapes everything gives the cosmos a kind of calm humility. As we imagine the spaces between galaxies filled with dark matter's hidden threads and stretched by dark energy's quiet expansion, we begin to see the universe not as static or empty, but as alive in a slow, continual transformation. Every moment, space itself is growing, carrying galaxies with it, like leaves on a rising tide. It is a process so vast and so gentle that it feels less like motion and more like breathing the universe's own rhythm, steady and continuous. Light has always been our only messenger. It is the one thing that connects us to everything else in the universe. Every star, every galaxy we have ever photographed, every faint glimmer recorded by a telescope, all of it comes to us through light. For most of human history, it was the only means we had to understand the cosmos. We cannot travel to the stars or touch distant galaxies, but we can collect the light that left them millions or even billions of years ago. That light is the universe's story, written in a language of wavelengths and colors. But even light has its profound limits. It travels fast, faster than anything else can move. Yet, the universe is vast enough to stretch that speed to its breaking point. When light leaves a distant galaxy, it begins a journey through actively expanding space across distances so immense that they change the light itself. By the time it reaches us, it has aged, its energy has faded, its color has shifted, and its message carries the marks of time. Much of what we call darkness is not a true absence of light, but light that has traveled too far to remain within the visible spectrum. Every photon that reaches your eyes tonight has lived a long and complicated life. The light from your lamp may be milliseconds old, but the light from the stars is ancient. The nearest star beyond the Sun, Proxima Centauri, is more than 4 years away at light speed. When you see its faint red glow, you are observing it as it was 4 years ago. The light from the Andromeda Galaxy left about 2.5 million years ago, when early human ancestors were first learning to use tools. The light from the most distant galaxies we can observe began its journey more than 13 billion years ago, long before the Earth even existed. It is a strange, quiet realization that when you look into the night sky, you are fundamentally looking through time. The farther you gaze, the older the universe you see. Each photon is a time traveler, carrying specific information about what the cosmos used to be. The journey those photons make is not through a fixed stage. Space stretches as the universe expands, and as it stretches, it drags the light along with it. This stretching increases the wavelength of light, shifting it toward the red end of the spectrum, a phenomenon astronomers call redshift. It is not because the light itself is slowing down. It always travels at the same speed. It is because the space it is moving through is actively expanding. Each wave of light gets stretched as the universe grows, and by the time it reaches us, its energy has decreased. A photon that left a distant galaxy as visible light might arrive billions of years later as infrared or even microwave radiation, too faint for our eyes to detect. This is a primary reason why so much of the universe is invisible to us. Light that began its journey long ago has been stretched so much that it no longer falls within the range of visible wavelengths. To detect it, we require telescopes that can see beyond what our eyes can into the infrared, the radio, and the microwave ranges. Instruments like the James Webb Space Telescope and the Atacama Large Millimeter Array all search for light that has been profoundly transformed by time and distance. What they find is that even the darkest parts of the sky glow faintly when examined deeply enough. The fading of light over distance is also due to the simple fact of spreading out. As a beam of light travels through space, the same amount of light covers a larger and larger area. The intensity drops, becoming weaker the farther it goes. For a galaxy billions of light years away, even its brightest stars are reduced to a mere whisper of light by the time they reach us. Most galaxies we detect are captured by detectors receiving only a few photons per second. Intergalactic space, although incredibly empty, is not completely transparent. Scattered clouds of gas, mostly hydrogen, drift between galaxies. These atoms can absorb or scatter light. The effect is subtle, but cumulative. Over billions of light years, these faint traces of matter act like a massive filter, removing specific wavelengths and slightly dimming the light that passes through. This absorption leaves a detectable fingerprint in the light spectrum known as the Lyman alpha forest, a dense pattern of absorption lines that informs astronomers about the structure and composition of the universe between us and the source. The darkness between galaxies is not silent. It is a record of the complex journey light has taken. Sometimes, entire regions of the universe seem to vanish behind curtains of opacity. In the earliest epochs, before the first stars and galaxies formed, the universe was filled with neutral hydrogen that absorbed nearly all ultraviolet light. Astronomers call this period the Cosmic Dark Ages, a time when the universe was opaque to visible light. Only after the first stars ignited, flooding space with radiation, did the hydrogen become ionized, allowing light to travel freely. That reionization marked the end of cosmic darkness and the beginning of the luminous universe we observe today. Yet, even now, the limits of visibility persist. Beyond a certain distance, light from galaxies is stretched so much by expansion that it fades into the infrared spectrum. Beyond that, it becomes microwave radiation, the same ancient glow we detect as the cosmic microwave background. That faint, nearly uniform radiation is the oldest light we can possibly see, released when the universe was about 380,000 years old. The photons we observe today from that era have been traveling for over 13 billion years, their wavelength stretched by a factor of 1,000. They are no longer visible light. They are a cold whisper from a time when the first stable atoms were forming. Every observation we make is bounded by that horizon, the surface beyond which light has not had sufficient time to reach us. The observable universe is defined not by where space ends, but by how far light has traveled since the beginning of time. Anything farther away exists, but we cannot see it because its light is still on the way, trapped by the relentless expansion of space. As the universe ages, that horizon continuously changes. More regions slip beyond reach. Light lost to distance becomes light lost to history. For astronomers, This fading of light is both a limitation and a scientific gift. It prevents us from seeing everything, but the way light stretches, dims, and changes tells us exactly how the universe works. Every shift in wavelength is a precise measurement of time itself. The further we look, the slower the pace of time appears. Distant galaxies seem frozen in their youth, their light arriving long after the events themselves have passed. In the deepest images taken by telescopes, a single patch of sky can reveal thousands of galaxies, some so faint that only a handful of their photons reach the detector after weeks of exposure. Those photons traveled through the stretching fabric of space for nearly the entire age of the universe. It is humbling to realize that our understanding of cosmic history depends on such fragile signals. Light does not only fade with distance, it also bends, slows, and scatters. Gravity itself can distort it. When light passes near a massive object, such as a galaxy cluster, its path curves. This bending gravitational lensing can magnify distant galaxies, allowing us to see farther than we otherwise could. Sometimes, the universe acts like a giant, natural lens, focusing light from the farthest galaxies through the gravity of those in between. Without this natural magnification, some of the most distant sources would remain invisible forever. Still, no matter how powerful our instruments become, there will always be light we cannot reach. Some of it is hidden by dust, and most of it has simply been stretched beyond detection, lost to the universe's own expansion. Over time, even more will slip away. As dark energy continues to accelerate the growth of space, distant galaxies will recede faster and faster. Their light will redshift beyond any possible detection. The cosmos will grow darker, not because it is dying, but because its light is drifting beyond reach. In that far future, only the closest galaxies, those gravitationally bound to us, will remain visible. The rest of the universe will fade into blackness. Future astronomers might look up at the night sky and see only a handful of galaxies, unaware that billions once surrounded them. They will live in a smaller, quieter universe, their horizon closing in as light continues to slip away. It is a profound thought, but the universe is not losing its light so much as it is carrying it farther away. Every photon that leaves a star continues forever, bearing the imprint of its origin. When we think about the spaces between galaxies, we tend to picture darkness, but much of that darkness is light in disguise light, too old or too stretched for our eyes to see. The universe is not truly dark. It is filled with ancient light we can no longer perceive. This faint, constant, invisible glow is everywhere. The CMB, the infrared hum of distant dust, the radio murmur of dying galaxies, all of it adds up to a background brightness that never entirely goes away. The Earth moves through this ocean of faint radiation every moment. The loss of light over distance teaches us a subtle lesson about perception. We think of seeing as instantaneous, a direct encounter with the present. But in cosmic terms, sight is memory. Every photon that reaches us is a record of the past. The farther we look, the older that memory becomes. There is no way to see the universe as it is right now. We can only see it as it was. Across the vast distances where the light fades and the voids stretch almost endlessly, there exists something faint, almost forgotten, yet absolutely essential to the universe's story. It is not a place, not a structure, but a pervasive presence. Astronomers call it the intergalactic medium, IGM. It is the substance that fills the spaces between galaxies, a ghostly blend of atoms, ions, and plasma that drifts through the cosmic web like a mist, so diffuse it might as well not be there. Yet, it is everywhere. When people imagine outer space, they tend to picture a perfect vacuum, an absolute emptiness. And it is true that compared to any environment on Earth, intergalactic space is staggeringly empty. But emptiness in cosmic terms is never truly empty. Even in the darkest regions between clusters, even in the heart of a great void, there are still atoms scattered through space, hydrogen, helium, and trace elements, remnants of the Big Bang still filling the universe. It is just that they are spread so thinly that we rarely notice them. In the depths of intergalactic space, there might be only 1 or 2 atoms, sometimes fewer, in every cubic meter. This sounds insignificant, but when accumulated over billions of light years, it forms an enormous ocean of matter, invisible to our eyes, but vast beyond imagination. This intergalactic medium, IgM, is one of the universe's quietest components. It does not shine brightly like stars, cluster into galaxies, or form planets. Yet, it holds the majority of the universe's normal, or baryonic, matter, the kind of matter made of protons and neutrons. Galaxies, despite their brilliance, contain only a small fraction of the total ordinary matter. The rest floats between them in this great diffuse reservoir of gas. For a long time, astronomers did not realize how important this medium was. When they counted all the visible matter in stars and galaxies, the numbers did not match what cosmological theories predicted should exist. A large portion of ordinary matter seemed missing. The scientific resolution was that the atoms had not vanished. They were simply too spread out and too hot to detect easily, hiding in the spaces between galaxies. New instruments allowed astronomers to find this missing material by looking not for light emitted by the intergalactic gas, but for light that passed through it. When light from a distant quasar, one of the brightest objects in the universe, travels across intergalactic space, it encounters patches of hydrogen gas. Each cloud absorbs specific wavelengths, leaving a distinct pattern of dark lines in the quasar's spectrum. This pattern, known as the Lyman alpha forest, acts like a barcode for the universe. Each line represents a separate cloud of gas at a different distance, allowing scientists to trace how the intergalactic medium is distributed. What they found was remarkable. The IgM is not uniform. It forms filaments and threads that mirror the cosmic web of dark matter. It is denser along the filaments, where galaxies cluster, and thinner inside the voids. The same structure that defines the arrangement of galaxies also shapes the invisible gas between them. This faint pattern is a preserved echo of the universe's earliest architecture. The gas's composition tells a story of cosmic evolution. Most of it is hydrogen and helium, the simplest elements left over from the Big Bang. But mixed within are trace amounts of heavier elements: oxygen, carbon, nitrogen, and iron. These heavier elements could not have formed in the Big Bang. They were forged inside stars and then ejected by supernova explosions and galactic winds. Over billions of years, galaxies have been slowly polluting the intergalactic medium with the products of their life cycles. In that sense, the space between galaxies is enriched with the ashes of countless generations of stars. This material eventually falls back into galaxies, fueling new star formation, making the IgM the continuous, slow bloodstream of the universe. One of the most fascinating aspects of the intergalactic medium is its temperature. You might expect space this empty to be uniformly cold, but it is not. The gas between galaxies can vary from a few thousand degrees to millions of degrees Kelvin, depending on its location. Near galaxies and along filaments, where matter is more concentrated, gravity compresses the gas and heats it through shocks and collisions. In these regions, the IgM becomes a tenuous plasma, glowing faintly in ultraviolet and X-ray wavelengths. Deeper in the voids, it cools, drifting closer to absolute zero. Detecting that faint warmth required decades of effort. Ordinary telescopes cannot see it because the gas is far too diffuse to emit visible light. Instead, astronomers use space-based observatories that detect ultraviolet and X-ray radiation. In the last few decades, scientists discovered an especially important part of this medium, known as the warm-hot intergalactic medium, or WIM for short. This is the portion of intergalactic gas heated to temperatures between 100,000 and 10 million degrees Kelvin. Despite its extreme heat, the WHIM is incredibly thin, a few atoms per cubic meter at most. Yet, when astronomers accounted for all the matter in the universe, the WHIM was found to contain the missing half of the baryons that had long eluded detection. The invisible became accounted for, not by changing theory, but by learning to see more softly using specialized instruments. When you visualize this vast, diffuse gas, it is hard to find a direct analogy. It is a plasma in the most tenuous possible state, a medium between being something and almost nothing. The intergalactic medium connects all galaxies, forming a continuous but almost intangible ocean. This invisible fog is not static. It moves, flows, and evolves with time. Along the filaments of the cosmic web, gas streams into galaxies, feeding their growth. At the same time, galaxies push gas back out into the IgM through powerful winds driven by supernovae or active black holes. This exchange of matter is called the cosmic baryon cycle. It is how galaxies breathe, drawing in fuel, converting it into stars, and exhaling enriched gas back into the universe. Even though we cannot see this gas directly, its influence is everywhere. It affects how galaxies form and determines how quickly new stars are born. Without the intergalactic medium, galaxies would run out of fuel. One of the great insights from studying the IgM is how interconnected everything is. Galaxies may look like isolated islands, but they are part of a continuous ecosystem, exchanging matter and energy across millions of light years. This circulation ensures that the universe remains dynamic. The intergalactic medium is also a kind of record of cosmic temperature and density. The patterns in its structure tell scientists when and how the first stars re-ionized the universe and when galaxies began to pollute their surroundings with heavier elements. Even in the most remote voids, traces of gas remain. The density may drop by orders of magnitude, but it never reaches zero. Space, it seems, refuses to be completely empty. Through the quiet stretches of intergalactic space, past the faint hydrogen gas and the distant glimmer of galaxies, there move things far smaller than stars, far faster than light's familiar companions. The universe, though vast and mostly empty, is never entirely still. Even across the greatest voids, invisible travelers pass, particles born in places of unimaginable energy racing through the cosmos at nearly the speed of light. They are the cosmic rays, the silent messengers of violent events scattered across space and time. Cosmic rays are atomic nuclei, electrons, and other high-energy particles that have been accelerated to tremendous speeds by powerful cosmic forces, such as supernova explosions, magnetic fields around black holes, and the powerful jets of quasars. They are the universe's restless travelers, never staying in one place. Every second, countless cosmic rays pass through the intergalactic medium. Most will continue indefinitely, their journeys stretching across billions of light years. A few will reach worlds like ours, colliding with atmospheres and splitting into cascades of secondary particles. They are invisible to our eyes, but they are everywhere, passing through the empty dark with energies so high that even our best particle accelerators on Earth cannot match them. The story of their discovery began much closer to home. In the early 20th century, scientists found that the ionization in the atmosphere increased with altitude. Whatever was causing it was coming from space. These mysterious high-energy particles were the first direct evidence that space itself was filled with invisible energetic visitors. Most lower-energy cosmic rays originate from within our own galaxy. Supernova remnants can accelerate charged particles to near light speeds. These particles then wander through the galaxy, bouncing from magnetic field to field. The higher energy cosmic rays, however, are harder to explain, as some carry energies millions of times greater than any produced by supernovae. These are thought to come from the most powerful engines in the universe: active galactic nuclei, quasars, and perhaps even the collisions of entire galaxies. Their precise origins remain uncertain. As they travel, cosmic rays interact with everything they pass, with magnetic fields, with stray atoms, and with photons of background light. Each collision can change their energy or direction. Over millions of years, their paths become tangled, making it almost impossible to trace them back to their source. They arrive as whispers from nowhere, carrying hints of the energetic processes that created them. Scientists have learned to read these whispers. By measuring their energies, we gain information about distant astrophysical events, the death of stars, the growth of galaxies, and the magnetic structure of the universe itself. They are messengers, bringing with them stories from regions we cannot see in light. When one of these particles strikes the upper atmosphere, it sets off a chain reaction, producing a shower of secondary particles that cascade downward. Every second, thousands of these particles pass through your body without harm. The air, the ground, and the sea are all continually touched by the faint aftershocks of cosmic rays that began their journey millions or billions of years ago. Cosmic rays play a subtle role in maintaining the ionization of interstellar and intergalactic gas. They may even affect the formation of clouds on planets. If you could see them, the space between galaxies would no longer seem silent. It would be alive with movement, thin, fleeting, but endless. The intergalactic medium is their highway. Because the gas between galaxies is so thin, cosmic rays can travel enormous distances without collision. The same emptiness that allows them to travel also isolates them, their fates governed by random encounters, ultimately crossing the entire observable universe and continuing outward. Among these cosmic travelers are also neutrinos, particles even stranger than cosmic rays. They are so small and elusive that they can pass through entire planets without interacting. Trillions pass through your body every second, streaming from the sun, from supernova explosions, and from the Big Bang itself. They are the ultimate invisible visitors, ghosts that slip through matter without leaving a mark. Unlike cosmic rays, which are charged and easily deflected by magnetic fields, neutrinos travel in straight lines from their sources. When we detect one, we are seeing a direct message from wherever it came. Detecting them, however, is incredibly difficult because they interact so weakly with matter. Most pass through detectors unnoticed. To catch even a few, scientists construct enormous observatories, tanks filled with ultra-pure water or ice, buried deep underground or beneath Antarctic glaciers. When a rare neutrino does collide with an atom, it produces a faint flash of light, visible only to sensitive sensors. From those flashes, scientists reconstruct the neutrino's origin and the energy it carried. Each one is a data point in the map of the invisible universe. Together, cosmic rays and neutrinos form a hidden layer of cosmic communication. They are not light, yet they tell us about things light cannot show. They carry information about violent processes, explosions, collisions, and decays that happen in places we may never see directly. When a massive star collapses in a distant galaxy, it sends out a wave of energy in multiple forms: light, gravitational waves, neutrinos, and cosmic rays. Light may fade or be absorbed, but some of those particles will continue, crossing the intergalactic medium and arriving long after the event itself has ended. Every particle that reaches us is a survivor of cosmic history. These invisible visitors remind us that the universe is not a quiet vacuum, but a medium filled with constant motion and exchange. The spaces between galaxies are not barriers. They are part of the same continuous field. Cosmic rays and neutrinos move through them as easily as sound moves through air, but without sound, without friction, and without slowing. They are the faint, constant heartbeat of the cosmos. It is humbling to realize how much passes through us unnoticed. The Earth is continually bathed in radiation from the cosmos. High-energy fragments silently rain down through the atmosphere. Yet, those same particles help us understand where we came from. Some of the isotopes they create are used to date ancient rocks and track solar cycles. Out in the intergalactic medium, their presence is even more profound, contributing to the temperature, the ionization, and the pressure of the space between galaxies. Over billions of years, these invisible travelers have helped sculpt the universe, transferring energy from one region to another, making the IGM a stage of ceaseless invisible activity. There are even higher mysteries among these travelers. Ultra-high energy cosmic rays, the rarest and most powerful of all. Their origins remain uncertain. Some may come from the spinning supermassive black holes at the centers of galaxies. Others may arise from processes that occurred only in the early universe, soon after the Big Bang. Their energies are so extreme that they challenge our current understanding of physics. When one strikes the Earth, it delivers as much energy as a falling pebble, but concentrated into a single atomic nucleus. These particles remind us that the universe still contains unknown mechanisms of power. We detect only the faintest echoes, but those echoes tell us that the cosmos is still far from quiet. In the great silence between galaxies, there is motion we cannot hear, radiation we cannot see, and matter we cannot touch. Particles born in ancient explosions race past one another, indifferent to the vastness around them. They will continue their journey until the expansion of space itself stretches them beyond reach. Their persistence proves that even in the most distant and desolate reaches of the cosmos, there is connection. Energy never truly stops. It moves, transforms, and passes on, linking galaxies through invisible chains of interaction. The universe may be mostly empty, but it is never still. The space around you is alive with motion, a continuous reminder that even emptiness is full of passage. There are forces in the universe that move quietly, without light, without particles, and without any visible sign that they exist. They are the echoes of gravity, the gentle waves that travel across the universe whenever something massive moves suddenly or violently enough to disturb the fabric of space-time. These waves are not made of matter or energy in the usual sense, yet they carry both. They are the universe's way of whispering about its own motions. The idea that gravity could make waves follows from Einstein's theory of general relativity. According to this theory, space and time are active, flexible entities that can bend and stretch. When two masses move around each other, the resulting distortion can ripple outward, carrying energy away as gravitational waves. These ripples are incredibly weak, even from the most extreme events. It took a century after Einstein's prediction for humanity to detect them directly. In 2015, scientists at the Laser Interferometer Gravitational Wave Observatory observed a faint signal that matched the merging of two black holes more than 1 billion light-years away. The detection confirmed that gravity itself travels in waves. Since then, dozens of gravitational wave events have been recorded, each one a message from the darkest, most energetic moments in the universe, the collisions of black holes, the mergers of neutron stars, and the violent deaths of binary systems. Unlike light or matter, gravitational waves do not scatter or fade easily. They pass through everything's stars, gas, and galaxies without slowing down or losing their shape. This means they carry pristine information from their source, unblurred by the long cosmic journey. When two black holes merge, the process releases more energy in gravitational waves than all the stars in the universe emit in light at that moment combined. Yet, because these waves spread across such a vast expanse, their strength is less than the width of a proton by the time they reach us. The energy of entire galaxies is carried as a whisper. These waves also come from everyday cosmic acceleration, forming a continuous background of gravitational noise that fills space. Astronomers call it the gravitational wave background, a steady hum of countless overlapping signals from across cosmic history. It is the faint vibration of the universe's structure, always present, always passing through us. Detecting that background is one of the great challenges of modern astrophysics. To hear the cosmic hum, we need instruments that can detect longer, slower waves. Pulsar timing arrays offer one method. Pulsars are rotating neutron stars that emit precise beams of radio waves. As gravitational waves pass between us and these pulsars, they slightly alter the timing of their pulses. By monitoring many pulsars spread across the sky, scientists can detect the subtle, coordinated shifts, the signature of gravitational ripples moving through the galaxy. Recently, hints of that background have begun to appear. This new form of astronomy is just beginning. Everything we knew about the universe once came from light, but now we are learning to listen as well as look. We are learning that the universe's deepest phenomena are not always bright. Some are completely dark, detectable only through the ripples they send across the cosmic fabric. In a way, gravitational waves connect everything. They are not limited by light's reach because they travel through space as a part of it. When a black hole merger happens, the resulting waves ripple outward in every direction, stretching the very coordinates by which distance is measured. For a brief moment, the entire universe participates in that single event. Even here on Earth, those ripples move through us, infinitesimal but real, changing the distance between every atom by a tiny fraction. The intergalactic medium, the cosmic web, and the dark matter scaffolds all feel these waves. They pass unhindered through gas, dust, and void alike. They are perhaps the purest expression of cosmic connection energy, traveling not through matter, but through the structure of existence itself. The universe is not a silent, static expanse. It is alive with motion, expansion, and vibration. Every gravitational wave is an echo of movement, a memory of something that happened far away and long ago. We cannot see them, but they are always passing through us. The Earth, the Sun, the Milky Way are all drifting in a sea of invisible motion, bathed in gravitational echoes that never stop. Among all the light that fills the universe, there is another kind of light, faint and forgotten, drifting in places where it should not exist. It is not attached to any galaxy or cluster. It floats freely, filling the dark spaces between galaxies with a dim, ghostly glow. Astronomers call it intracluster light, but the name barely captures what it is. These are the traces of orphan stars, stars that have been violently stripped from their home galaxies and left to wander the intergalactic medium. The light of these wanderers is difficult to see, almost invisible against the background darkness. It's not the bright light of galaxies or the sharp spark of individual stars seen through a telescope. It is a soft haze spread thinly across enormous distances, faint enough that it disappears if you try to look at it directly. Only through extremely long exposures and careful subtraction of every other source of light can astronomers begin to detect it. But it is there, a low, diffuse glow between the galaxies of clusters, the scattered remnants of countless stellar lives. These orphan stars are born from violence. Galaxies do not drift peacefully forever. They move through space like ships in a crowded ocean, pulled and distorted by the gravity of others. When two galaxies pass near each other, their mutual gravity can tear away stars, gas, and dark matter, stretching them into long tidal streams that curl through intergalactic space. Over billions of years, as clusters of galaxies interact and merge, these tidal encounters build up a population of stars no longer gravitationally bound to any single galaxy. In the largest galaxy clusters, this stripping process happens constantly. Galaxies orbit the cluster's center, their outer regions stripped by gravitational tides. The stars that escape become unbound, continuing their orbits not around any single galaxy, but around the cluster as a whole. Collectively, they form the intracluster light, ICL, a faint, diffuse glow that connects the galaxies in a cluster like mist surrounding distant lamps. When astronomers measure this light, they find it accounts for a surprising fraction of a cluster's total luminosity, sometimes as much as 20 or 30%. That means a significant portion of all stars in a cluster are wanderers, no longer part of any galaxy. They drift in the vast spaces between, forming a stellar population that few will ever see directly. These orphan stars are not all the same. Some are old red giants, stripped long after their galaxies have aged. Others are young, pulled out along with gas clouds that can still form new stars in the intergalactic medium. There are even planetary nebulae and white dwarfs cooling silently between galaxies. Each one is a piece of galactic history, violently torn loose and set adrift. The light they emit is faint but beautiful in its persistence. Because they are scattered so widely, the glow they produce is diffuse, almost like fog illuminated from within. When astronomers use sensitive instruments to image a cluster for hundreds of hours, the result reveals this soft light spreading outward between galaxies, faint but continuous. It gives the impression that the cluster is wrapped in a gentle halo, a visible sign of all the interactions and collisions that have taken place over billions of years. To detect such faint light requires immense patience and precision. Specialized instruments are needed to block out brighter sources and focus on the faintest possible background. Observatories like the Hubble Space Telescope and the James Webb Space Telescope have revealed it with more clarity than ever before. In deep images of clusters, filaments of ghost light thread between galaxies, marking the paths of tidal debris, the footprints of ancient encounters. Each faint stream tells a story. Somewhere long ago, two galaxies passed close enough for their stars to be pulled apart. What began as individual acts of gravitational violence became collectively a quiet glow. The cluster's diffuse light is a record of all its collisions, preserved in photons that continue to travel long after their sources have been forgotten. For scientists, studying this ghost light is a way of understanding how galaxies evolve in dense environments. The fraction of intracluster light reveals how much interaction and merging has occurred. Clusters with brighter diffuse light tend to be older and more dynamically active, their galaxies having collided many times. By measuring the light's color and distribution, astronomers can estimate how long ago certain events happened and how efficiently stars are stripped from their galaxies. There is another layer to this story. Not all orphan stars are created by tidal forces. Some form directly in intergalactic space. When gas is pulled out of galaxies during collisions, it can remain suspended in the cluster's gravitational field, slowly cooling and forming new stars of its own. These newborns are truly intergalactic stars that have never belonged to any galaxy. Born in the thin gas between them, they burn quietly in isolation, their light blending into the faint background glow. Even in its solitude, the orphan star is bound to the cluster's gravity, orbiting alongside millions of others that share its fate. Though each one is dim and far apart from the others, their combined light becomes visible when added over vast scales. The cluster's ghostly glow is the sum of countless solitary lives. Their presence is proof that galaxies are not eternal. They change, merge, lose pieces of themselves, and leave behind traces in the spaces between. Every diffuse glow is evidence of motion and transformation. The ghost light bridges the gap between galaxies, showing that even their losses become part of something larger. The light does not vanish when a star leaves its home. It continues traveling through space, illuminating the dark between galaxies. Even stripped and scattered, the matter and light remain within the cosmic web, linked by gravity to everything else. In the largest clusters, this intracluster light can extend for millions of light years, a faint ocean of photons surrounding every galaxy. The cluster would not appear as a collection of separate islands, but as a continuous region of soft, diffuse light punctuated by brighter cores. The orphan stars give the universe a kind of quiet continuity. They link the violent past of galaxy formation with the tranquil present. What makes this light particularly subtle is how near it is to being invisible. Even when we detect it, it is so faint that a single miscalibration can erase it from the data. It is a reminder that much of the universe exists right at the edge of perception. The ghost light is there, all around us, but only the most patient instruments can see it. Some scientists suspect that intracluster light extends even farther than we have measured, not just between galaxies and clusters, but along the filaments connecting clusters together, creating bridges of faint starlight across the cosmic web. If that is true, then the universe is even more interconnected than we imagined. The light between galaxies would not just be a byproduct of collisions. It would be a network of faint illumination tracing the very structure of the cosmos. Out in the deep fabric of the universe, hidden behind the light of galaxies and the quiet glow of wandering stars, lie regions where the rules of space and time bend completely. These are the black holes, places where gravity becomes so strong that nothing, not even light, can escape. They are the endpoints of matter, the remnants of collapse, and the anchors of galaxies. A black hole is not a thing so much as a region, a place where the geometry of space is twisted inward on itself. It is defined not by what is inside, but by what cannot get out. The boundary around it, called the event horizon, marks the point of no return. Once anything crosses that boundary, its fate is sealed, flowing inward toward a single point, compressed beyond any known limit. The existence of black holes is one of the most thoroughly confirmed predictions of general relativity. We have observed stars orbiting invisible companions whose masses are millions of times that of the Sunday. We have seen X-ray flares from gas spiraling into unseen centers. Most strikingly, the Event Horizon Telescope captured the image of a black hole's shadow, the dark silhouette surrounded by a glowing ring of light in galaxy M87, showing exactly what Einstein's equations predicted. Black holes are among the most important players in the universe's story. Almost every large galaxy has one at its core, a supermassive black hole, millions or billions of times heavier than the Sunday. These giants shape their galaxies through their immense gravitational influence. When gas falls toward them, it heats up, creating powerful jets of radiation and particles that can extend for thousands of light years. Those jets, in turn, regulate star formation, sculpting the evolution of the galaxy itself. Black holes do not just consume, they organize. The regions around them are among the most energetic in existence. As matter spirals inward, it forms an accretion disk, a swirling ring of gas moving at nearly the speed of light. Friction and magnetic turbulence within the disk heat it to millions of degrees, causing it to radiate intensely in X-rays and gamma rays. Some of that energy escapes along the black hole's rotational axis, forming narrow beams that shoot into intergalactic space. These jets can travel across the cosmic web, carrying energy from the galaxy's core into the intergalactic medium, stirring and heating the gas between galaxies. In this sense, black holes connect the smallest and largest scales of the universe. What happens in their immediate vicinity affects regions hundreds of thousands of light years away. The quiet glow of the intergalactic medium, the temperature of cluster gas, and the pressure that shapes galactic evolution are all influenced by the energy released near black holes. Yet, despite all we know about them, the centers of black holes remain fundamentally mysterious. General relativity predicts that inside the event horizon, matter collapses into a singularity, a point of infinite density and zero volume. Physics, as we know it, cannot describe such a place. The equations that describe gravity, energy, and space-time all fail there. This mystery has led to speculation that black holes might not simply be endpoints, but transitions that they could connect different regions of space-time, or even different universes, theoretically forming wormholes. Whether or not such connections exist, black holes already serve as bridges between eras of time. When we observe them, we are looking at the end of one process and the beginning of another. The collapse of a massive star transforms it into a phenomenon that affects the structure of an entire galaxy. Energy flows outward, even as matter flows inward. The interplay between black holes and their environments is a delicate balance. On one side, gravity pulls relentlessly inward. On the other, magnetic fields and radiation push outward, carrying energy back into the universe. The most powerful of these are the supermassive black holes at the centers of active galaxies, known as quasars. They are so bright that they can outshine all the stars in their host galaxies combined. Quasars are the beacons of the early universe, showing us what it looked like when galaxies were young and black holes were growing rapidly. As we look deeper into the past, we find that black holes and galaxies seem to evolve together. The mass of a galaxy's central black hole is tightly correlated with the mass of its bulge, suggesting that the two grow in tandem. This feedback loop continues over cosmic time, linking the smallest scales of gravity to the larger scales of structure formation. For all their power, black holes are astonishingly simple in one sense. According to physics, they can be completely described by just three properties: mass, charge, and spin. All the other details of the matter that formed them are lost behind the event horizon. That simplicity raises profound questions about information. When something falls into a black hole, does the information about its state vanish, violating a core principle of quantum mechanics? This is the black hole information paradox, one of the deepest unsolved problems in theoretical physics. Some theories suggest that black holes are not truly eternal. Through Hawking radiation, they slowly lose mass, shrinking until they evaporate entirely. While this process takes timescales vastly longer than the current age of the universe, it implies that even these giants will eventually fade. If that future comes to pass, black holes will be among the last active structures in existence, slowly radiating away their energy, marking the universe's final era. The energy released in their final moments will spread outward, adding to the background glow that persists even in near silence. In that sense, black holes and the bridges they might form are not opposites of creation, but expressions of it. They are part of the same ongoing process, one that turns collapse into motion and silence into connection. They are the unseen hearts that keep the cosmic structure coherent even across the largest scales. It is strange that in our quest to understand the universe, we constantly return to metaphors of sound. We talk about echoes, waves, vibrations, and harmonies. Even though the cosmos is truly silent, we describe it using the language of hearing. Perhaps this is because hearing is how we experience continuity and duration. Light gives us the shapes of things, but sound gives us time unfolding. And the universe, for all its stillness, is fundamentally about duration, about events unfolding across immense timescales. If you were to drift endlessly through intergalactic space, through that perfect silence, you would not feel isolated. You would feel surrounded by motion too slow to sense, by light too faint to see, by gravity too gentle to notice. The silence would not be an absence, but a medium, the necessary quiet in which everything else happens. And if one could understand it, the silence itself is a conversation, an ongoing dialogue between energy and emptiness, between motion and stillness. The sound of silence in the universe is not something we can hear, but something we can precisely understand. It is the steady background against which all else plays out. It is the calm that allows light to travel, matter to form, and time to flow. It is the necessary space that holds the story, not by filling it, but by allowing it to unfold. As we conclude our journey through the dark, quiet cosmos, this silence follows us, vast, patient, and full of hidden rhythm, waiting to be understood by those who can listen without requiring to hear. After drifting through the vastness of the cosmos, across galaxies, through invisible threads of matter, through waves of gravity and silence itself, it can feel strange to turn the view back towards something small. This single planet, this brief life, this narrow slice of experience, and yet, this is the only scale from which we ever perceive the universe. Everything we know about distant galaxies, black holes, and the expansion of space is filtered through the limits of human senses, human tools, and human imagination. We are small, but through understanding, we reach outward farther than our size would ever suggest possible. When you look up at the night sky, you see light that has traveled unimaginable distances. You are standing on a planet, orbiting a modest star in a spiral arm of a galaxy among hundreds of billions of others, all held together by invisible matter and energy. Yet the act of looking, of observing and wondering, connects you directly to that immensity. The light that enters your eyes carries information about events that happened before humanity existed, before the Earth existed, before even the sun had formed. That connection, fragile as it seems, places us in the center of understanding, even if we are not in the center of the universe. The physical laws that govern the fall of an apple or the swing of a pendulum are the exact same ones that shape galaxies and determine the fate of the universe. The same gravity that holds you to the Earth governs the motion of stars. We are made of the same matter, following the same rules, part of the same unfolding story. It is easy to feel small against the cosmic scale, but size alone does not determine significance. The universe is vast, but it is indifferent. Meaning does not emerge from scale. It emerges from awareness. The ability to observe, to ask questions, to interpret light and motion, that is what gives structure to experience. The cosmos would continue without us, but without consciousness, there would be no understanding of what it is. We are, in a sense, the universe becoming aware of itself. The human brain is a structure of staggering complexity, built from atoms, carbon, oxygen, nitrogen, iron, that were once forged in ancient stars. Those atoms once drifted through interstellar clouds, perhaps part of the very intergalactic medium we have described. Over billions of years, gravity gathered them into new systems, new worlds, and eventually into life. Each neuron that fires inside your mind is the descendant of a process that began in the heart of a star. That contrast between scale and understanding is one of the most beautiful aspects of existence. The universe operates across distances and times we can barely imagine. Yet the same laws that shape galaxies also allow molecules in a brain to form thoughts about them. From the human perspective, we stand at the intersection of the smallest and largest scales. We can look inward toward the quantum and outward toward the cosmic. Both directions lead to the same mystery: how complexity arises from simplicity. When scientists measure the universe, they use numbers that stretch far beyond normal experience. A light year, for instance, is nearly 10 trillion kilometers. A billion light years is a distance so large that even light traveling at 300,000 kilometers per second would require a billion years to cross it. Against that background, the human lifespan is almost nothing. Yet, in that short time, we have measured the age of the universe, mapped the galaxies, detected gravitational waves, and photographed black holes. We have turned curiosity into an instrument powerful enough to reach the edge of the observable. The atoms in your body, assembled into a living person, are arranged in a way that allows you to perceive and understand the very forces that created them. You can trace your existence back through planetary formation, through the birth of the sun, all the way back to the first few minutes after the Big Bang. In a very literal sense, you are made of the universe's memory. Yet, for all our insight, we still experience life at a human pace. Time flows for us in heartbeats and breaths, while cosmic time moves differently. Even the speed of light seems slow when stretched across cosmic distances. The light from a distant galaxy may travel for billions of years, only to end its journey in a single instant when it strikes your eye. The human scale is not wrong. It is simply one point among many. The universe contains everything from the subatomic to the galactic. We inhabit a narrow middle ground, large enough to perceive, small enough to think. In that middle ground, complexity flourishes. The human scale is where the universe becomes personal. Our smallness is not a limitation, it is a perspective. From where we stand, we can see the largest structures in existence and infer the smallest particles that form them. The human scale connects the infinite with the immediate. We see only a narrow band of the electromagnetic spectrum and hear only a limited range of frequencies, yet our experience is rich because our imagination expands it endlessly. That ability to build models, to ask questions, to picture what we cannot touch, is what makes our scale meaningful. In just a few thousand years, we have gone from staring at the stars with wonder to understanding how they shine. We have learned that the Earth is not the center, that the Sun is one of countless stars, and that those stars form galaxies that stretch beyond number. We have discovered dark matter and dark energy, forces that make up most of existence but remain invisible. Each discovery expands the boundary of what we know, yet each one also deepens the mystery. The more we learn, the more we realize how much lies beyond our reach. Knowledge turns distance into intimacy. The universe may not know we exist, but through observation, we make it known. The human scale is where comprehension happens, where the immeasurable becomes measurable. Every piece of knowledge we hold, every constant, every law, every measurement has been built within the limits of human perception. We are not outside the universe observing it. We are inside it, made of it, and thinking about it from within. That recursive loop matter that studies itself might be the most extraordinary structure of all. The human scale lies at a point of balance. It is the region where complexity peaks, where physics becomes chemistry, chemistry becomes biology, and biology becomes thought. It is the doorway through which the universe perceives itself. We exist at the intersection of knowledge and mystery, small enough to feel wonder, large enough to seek understanding. It is strange to speak about the universe for so long, to drift through the light of galaxies and the silence of voids, and then to arrive back here. We have learned that the vast stretches of apparent nothingness between galaxies are not nothing at all. They are filled with light too faint to see, with matter too thin to touch, with energy too quiet to feel. What lies between galaxies is the same thing that lies between thoughts and between moments. Connection, a continuous fabric that never truly empties, no matter how far it stretches. You could call it stillness, but it is not the stillness of rest. It is a dynamic quiet, a kind of equilibrium that lets everything else exist. Stars form and fade, galaxies drift apart. Matter cycles through creation and decay, but the background of it all remains constant, wide, and patient. The universe does not need to hurry. It has all the time there is. When you close your eyes, the darkness is not empty either. It is full of faint light, still reaching you from everywhere. Light that began its journey long before there were eyes to see it. Every photon carries history. The darkness that surrounds you is full of ancient messages moving silently through space, you are always within that field of light. If we could remove all the noise of our own existence and float in the intergalactic void, we would find a silence unlike any other. No wind, no echo, no sound at all, and yet it would not feel empty. There would be a faint glow in every direction, a barely perceptible background from the first light of the cosmos. It would be like floating in the memory of creation. That is what the universe looks like when everything else is stripped away. A calm sea of old light stretching infinitely, timeless and slow. The energy that animates a living body is not separate from the energy that drives the stars. The chemistry that keeps you alive is the same chemistry that unfolds in distant nebulae. You are made of recycled starlight, from the dust of generations of cosmic events. This connection does not need to be mystical to be profound. It is physics, chemistry, and biology, the natural flow of matter and energy through time. The universe does not feel far away anymore. It feels immediate, present, not something you look at, but something you are inside of. Every breath, every pulse, every slow rhythm of your body mirrors the rhythms of the cosmos. You are not separate from it. You never were. The same calm that fills the universe can fill your mind now. The universe is vast, but it is also here, within you, around you, connected in every direction. The scale of the human world is the doorway through which the universe perceives itself.